Hello everyone. So in previous video, we'll discuss the class regarding to introduction to VLSI. So in that class, I'll cover the topics related to what is VLSI and why VLSI is important nowadays and what are the careers in VLSI. After that, how a silicon wafer is extracted from sand and all. So after that, I'll discuss the things about MOS transistor cross section. What are the major differences between PMOS and NMOS? And after that, how a complementary MOS is created by using NMOS and PMOS. So after that, I'll post some questions also. What are the major differences between front end and back end? And what are the major steps involved in VLSI design flow? So if anyone is new to this channel and new to this video, please observe those videos also. And if anyone knows the answer for the questions, please comment down. Okay, let's start today's class. Today's class is also regarding to introduction to VLSI, but today we are discussing. Let me share my screen, guys. 1 minute. Yeah, sorry. Okay. What are the major differences between front end versus back end, right? So in front end, it designs the functionality. I'll discuss these things. In front end, it designs the functionality. 1 minute. Let me draw. Consider a OR gate. Okay. OR gate. Sorry. OR gate. Okay. We are having inputs A and B and output Y. Everyone knows the truth table for OR gate, right? What is the logic of OR gate? 0, 0, 0, 1, 1, 0, and 1, 1. What is the logic for OR gate? Any one of the input is high, it gives output as 1, which means high, right? So in both of these cases, both in both three cases, we are having 1 as a high. So we are getting output as high, right? I think you guys are very familiar with these things, with the functionality of OR gate and all. So now coming to clock. Okay. Okay. So this one is a clock. So A, B, and Y are my inputs, right? When what is the first input of A? 0, right? So up to this position 0 and B also 0, right? In this case, we are getting output as 0. Okay, 0. And after that, another input, this one also 0. And here, high, 0, 0. A is 0, B is 0. At this case, we are getting output as 0. And after A0, B1, at that case we are getting output high. So here high. Okay. And after that A output changes. Ayo, sorry. Okay. Here my input is high, right? Up to this I'm getting. After that also my input is high. Okay, no problem. Please try to understand. Okay, you guys should know about the functionality of OR gate, right? Okay, deleting all these things. Okay, so in front end, we are designing the functionality by using the RTL coding and all, by using hardware description languages. We are writing the logic for that OR gate. What is the logic for OR gate? I'll discuss now itself. So when any one of the input is high, our output is also high, right? So we are writing the functionality of that logic in front end, and in back end it makes physically real on silicon. So we are placing that OR gate on a chip. So consider this one as my silicon chip. So in this place I'm placing that OR gate in backend flow. So front end is completely related to designing the how we are specifying the inputs, and how we are writing the logic, how we are giving clocks and all the verification is done in front end side, and in back end side completely physical design flow. So how we are placing the things, how floor plan is done, how we are placing macros, how we are giving power, and all these things are covered in backend. Okay, so observe here. So in front end we are giving specifications, how that OR gate is works and all. Consider one block. So if firstly think this one is a dummy block. So tool don't know how the block is works and all. So at that case we are giving some specifications to this block, how the block is working and all. So we are giving some specifications. So after that RTL people starts working on that logic, how works on that specifications, we are uh, how we are writing the code by using those by using Verilog and VHDL codes, how we are writing the code to that according to that specifications. Okay, after that logic design, we are designing the logic, and after that we are simulating that logic by using clocks. I'll draw the clock thing, right? So we are observe the simulations and we'll verify those logic. So after that we are giving that complete thing to backend people. So here is the main physical design flow is started from after the simulations of that logic design. So backend people works is starting from physical design. So in physical design, they are starting from floor plan, how they are placing the blocks and all, and verification and implementation. All this work is done by backend people. Okay. After that, front end people are works at higher abstractions. They don't know the inner side of the logic. So consider one OR gate, right? Consider one OR gate. The people know about the how a OR gate logic is works and all. They don't know how in OR gate also they OR gate consists some transistors, right? So front end people don't know how these transistors and working and all. So front end people are works at higher abstractions. Abstractions means it hides the information. Okay, it shows only the main things. Okay, and backend people works at the physical lower physical levels. So backend people complete work is they works completely on physical design flow, right? How we are placing the things and all. So after that, front end people verifies RTL code and a technology mapped gate level nest list. The output of front end people, they are works up to creating gate level netlist. This gate level netlist is we are giving input as input to the physical design people, which means backend people. We are giving main main input to the backend people is this gate level netlist, right? So after that, backend people works up to they are generating GDS2 file. Okay, I'll explain it further for in future classes. What is this GDS2 file and what is the gate level netlist and all. Don't confuse. So after observe this one. So this is the flow. Okay. First one is specifications. We are giving specifications to that block and write RTL people write the code for that logic by using Verilog and VHDL. And after that functional verification simulation is done for that logic. At synthesis stage, what is the main purpose of synthesis? At synthesis, we are translating our RTL level code to gate level netlist, right? Gate level netlist. So after synthesis, we are getting output as gate level netlist, right? So this is the complete front end front end flow. And coming to this back end flow, here first step is floor planning. So we are defining our core area and die area. Uh, After that, height and width of the chip, and after that we are placing the things, and we are giving clock by using clock tree synthesis. After that, routing means connecting to connecting one block to another. If any logic is there in between both the blocks, so we are connecting both the two blocks. After that, physical verification, in that DRC and design rule checks and layout versus schematic checks also done at this physical verification stage. After that, GDS2 is the output file for this backend people. Okay, so this is the major differences between front end and back end. Okay. After the technology node, what is technology node? So it is the smallest feature size. You guys know about as technology decreases, our gate length also decreases, right? So technology node means it is the smallest feature size. That means gate length. Consider this one. Consider this one as a MOS. Here, source and drain. So here we are having gate, right? Gate terminal. So as technology decreases, this gate length also decreases. Are you guys are agree with this part? Right? It is the smallest feature side manufacturable in a CMOS process in nanometers. Actually, technology node is defined in nanometers. So as technology decreases, this gate length also decreases. Okay. A smaller node means more transistors per chip. What is the meaning? Okay. If you are having small node means that gate length. Okay, I'll show. Consider this one as a small node and this one as a big node. Okay, large node. So if this is the size of my transistors, what I am placing in small node, if my gate length small means that transistor size also decreases. So I can place more transistors on the same place. But coming to larger nodes, bigger nodes, my transistor size is big because my gate length is big. So here, this is my source and this is my drain. Observe here, here my gate length is increases, right? Compared to this one. Here my gate length is increases, right? This one, my gate length is increases, which means when gate gate length is increases, my transistor size also increases. So uh, coming to these two things, I'm having same size of the chip, but I'm placing more transistors here in smaller nodes compared to larger nodes. Why? Why? Because of gate length, right? See here, I'm having 132 7 nanometers technology nodes. So in this place, we are placing only few amount of transistors. Why? Because we are having the gate length is high for what? Higher technology nodes, right? Gate length is high. So in that case, we are placing only few transistors. So coming to this one, 7 nanometers, we can place more transistors, millions or billions of transistors on a single chip, right? Okay. A smaller node, my transistors density increases, which means we can place more transistors on a small place, right? Transistor density is increases. And after that, performance increases. By performance is increases, we can place more transistors, right? If transistors increases means our performance also increases. Because if consider an example, if one worker is constructing a wall, okay, so that guy construct that wall in 4 days, but we are having two workers, we they can construct that wall in 2 days itself. So here performance also increases, we can save the time also. So same case here, as transistors increases, transistors count increases, or performance also increases, right? Okay. And as performance increases, our power will decreases. Okay. Why power is decreases? Our gate size is decreases. Gate length. Gate length is smaller nodes, right? So as gate length decreases, our gate capacitance also decreases, right? And after that, we are having shorter wires also. When we are placing transistors near to each other, so at this case, our routing resources also decreases, right? That's why power also decreases and fabrication. But here, observe this one. when we are having smaller nodes, fabrication complexity increases. How? We are having more number of transistors at a small place, right? So at that stage, complexity increases and cost also increases. Okay, because we are having more transistors, right? More resources. We are using more resources. At that stage, cost also increases. And 1 nanometer, 1 nanometer is equals to how many meters? Anyone knows? How many meters? If anyone knows the answer, please comment down. Question mark. Anyone knows the answer? 1 nanometer is equals to how many meters? Okay, note this one as a homework. Let me comment down. Okay. Why we use technology nodes? Nodes defines a complete ecosystem, right? What it means? Complete ecosystem means, sorry, it defines the complete design rules, libraries, what we are using libraries in that, and what are the design rules, how a chip is fabricated, all this process, okay, and what is the yield and reliability, okay. So all these things are mentioned in technology nodes. If consider one technology node, 28 nanometers or 28 nanometers, right? So by listening this word itself, we can say that okay, this chip performance is like this chip consumes this much of power, and this chip uh, yield is this much, reliability is this much. So we can say by using the technology nodes, okay. For this purpose, we are mainly having technology nodes, okay. Smaller node allows more per wafer. I said you earlier also. So if you are having more chips on a small place, so at that stage, we can we can get more performance on all. So, and if you guys know about any foundries, any technology providers, I you guys listen this word TSMC. Anyone knows what is the full form of TSMC? This is the one of the leading technology provider nowadays. TSMC. Taiwan Semiconductor. What? Comment down, guys. What is the full form of TSMC? And we are having another foundries also like Intel, Intel and Samsung. So all these are the foundries. And another one, what is that? Global Foundry also. We are having Global Foundry also. Okay. TSMC means Taiwan Semiconductor Manufacturing Company. I think so. Yes. And this is the main use of technology nodes. Okay. So these are the main differences between smaller nodes and bigger nodes, guys. So coming to smaller nodes, in smaller nodes, our performance increases. Why? Because we are having more transistors, right? High performance. In smaller nodes, high performance is there because more transistors, more number of transistors. Transistors count increases. But low power. Okay, and it consumes low power also. Why? As gate size decreases, gate capacitance also decreases, right? And routing resources, shorter wires, it allows only shorter wires because blocks are play, placing near to each other. So at that case, we can it consumes only less power. Okay. So in small place itself, we are placing more transistors, right? That's why our performance also increases, but much higher cost. Why? We are having more transistors. So for that more transistors, our cost also increases and complexity also increases. Okay. Coming to bigger node, low performance because less number of transistors. We are placing only fewer transistors, and here power also increases, but cost decreases and design also decreases. Why? Because here complexity is reduces, right? And this is the major differences between smaller nodes and higher nodes. In bigger nodes, transistors, 1 minute. So this one is considered bigger node and smaller node. These are the properties. Okay. First one is properties. Properties, bigger node and smaller node. So coming to transistor size. So coming to transistor size, for bigger nodes, my transistor size is large, right? And coming to smaller nodes, transistor size is small because of gate length, right? And after that, chip area. Okay, chip area. Here, my chip area is large, right? Here, chip area is small. Why? Consider 200 transistors. Okay, we can place these 200 transistors in a single chip, where in smaller nodes, but in bigger nodes we are dividing the transistors into two chips, and we are placing 100 transistors in one chip and another transistors in another chip. So at this stage, cost also increases, and these are the disadvantages of bigger nodes, right? So this is the chip area. So for bigger nodes, chip area is large, and for smaller nodes, chip area is small. And coming to speed, this one is the main thing, right? So speed for bigger nodes, my speed is low because we are having low transistors, right? So when you are having low transistors, our speed also low. So here speed is high. Okay. And coming to cost, you guys know about this thing. So bigger nodes, cost is low, and for smaller nodes, cost is extremely high, right? Nowadays, you're using smaller nodes only for better performance. Okay. And that's it for today, guys. And these are the questions. Please note down the questions. If you guys are know about these answers for these questions, please comment down. What is the difference between 7 nanometer and 14 nanometer? And why don't all chips use the smallest nodes? So nowadays we are, I said you earlier, like we are present we are using 7 nanometers, right? Which means a smaller nodes, right? So even we are having smaller nodes also, for some purposes and all, we are using bigger nodes also. So why? Because why don't all chips use the smallest nodes? So for some chips we are using smaller nodes, and for some chips we are using bigger nodes. Why? So if anyone knows these answers, please comment down. And that's it for today, guys. If anyone having any doubts, please let me know in the comment section or in Telegram channel. Please take it as serious thing. Try to work it on more. Learn PD, learn the basics. Okay, thank you. That's it for today. Have a great day.